Have you ever stopped and thought, how machines could go beyond just recognizing things? Like not just seeing a cat, but actually imagining a cat.
Or composing music, maybe? Something entirely new.
Exactly. Not just analyzing Mozart, but writing like Mozart. It
Yeah.
feels like this huge leap, doesn't it?
Yeah.
From just processing probabilities
Yeah.
to something that feels, well, creative.
It really is. And that's what we're diving into today, right? This whole world of generative models.
Yeah, absolutely. We want to unpack how deep learning lets AI move past simple prediction, classifying this or predicting that, and actually start producing things, novel things.
Things that can sometimes really surprise you. Images, sounds, text. It's learning the underlying structure, the fabric of the data itself.
And to help us navigate this, we've got some great sources lined up. We're pulling from Andrei Burkov's 100-page machine learning book, Martin Ford's Architects of Intelligence, notes from Andrew Ney.
Plus, insights from a whole range of AI pioneers will try and guide you through the art and, I guess, the science behind this machine creativity.
Okay, so maybe we should start at the beginning. To get how machines create, we first need a solid grip on how they learn in the first place.
Good idea. So think back to supervised learning. That's kind of the foundation for a lot of ML. You have labeled data, right? You show the machine examples.
Like here's a description of a person, their features, and here's whether they developed cancer or not.
Exactly. You input that feature vector, and the model outputs a probability. The whole game there is finding the right parameters, the right settings for the model.
Like the WMB you see in things like support vector machines.
Precisely. You're essentially trying to draw the best possible line or boundary to separate the different classes of data. Make that separation really clear.
So it's not just any line. It needs to be the optimal one to give you confidence.
Right. And the intuition, especially with something like an SVM, is to push that boundary as far away as possible from the closest data points on either side.
Maximizing the margin.
You got it. That makes the decision boundary more robust, less likely to mess up on new data it hasn't seen before, assuming, of course, the classes can be separated cleanly.
So the goal isn't just to memorize the training data, which would be easy but useless.
Totally useless for anything new. It needs to understand the underlying pattern, the probability distribution of the data, even if we don't know that distribution perfectly ourselves. We just have the sample, the data set.
Okay, that makes sense for prediction.
Yeah.
But isn't there a catch? A lot of the big successes in deep learning, especially pattern recognition, seem to need just enormous amounts of labeled data.
Oh, absolutely. That's a huge bottleneck. Andrew Deng talks about this a lot, how needing so much data is a major limitation today.
And Yoshua Bengio echoes that, right? Saying something like, we can't realistically label everything in the world.
Exactly. We can't spoon-feed the machine every single detail. It points to a big challenge. How do we move beyond needing these massive human-labeled data sets? How do machines learn more like us, with less direct supervision?
Which feels like the natural stepping stone towards creativity, doesn't it? If it can learn more from raw observation.
Precisely. And that brings us nicely to this really cool idea, autoencoders.
Right. So instead of predicting a label, what if the machine's task was just to reconstruct its own input?
Exactly. That's the core idea. An autoencoder is usually a feed-forward neural network. Information flows one way, but it's trained in this unique, self-supervised way. The input is the target output.
So you feed it, say, an image, and you tell it the right answer is this same image.
Yep. A pair, like input, make the output as close to the input as possible.
Okay, that sounds almost too simple. Like, it's just learning to be a copy machine. How does that help with generating something new?
Well, here's the clever bit, the structure. Often these networks look like an hourglass. There's an encoder part that takes the input, maybe a big complex image.
High-dimensional data.
Right. And it compresses it down, squeezes it through a much narrower bottleneck layer in the middle. This bottleneck holds a compressed representation, an embedding.
A sort of summary or essence.
That's a great way to put it. Then the decoder part takes that compressed embedding and tries its best to reconstruct the original input from just that summary.
I see. So by forcing it through that bottleneck, you're making it learn what's really important, the core features, not just superficial details.
Exactly. It has to learn a meaningful, a compact representation. Like, you could theoretically encode MNS handwritten digits pretty well with maybe only 10 units in that bottleneck. It forces efficiency.
Wow. Okay, so it distills the essence. And that distilled essence, that embedding, that's where the magic happens for generation.
That's where a lot of the potential lies. You can use these learned representations for things like anomaly detection spotting things that don't fit the normal pattern the autoencoder learned.
Like finding weird credit card transactions.
Exactly. Or, and this is key for creativity, you can start to play around within that embedding space. You can take the embeddings for two different inputs, say two different faces, and kind of smoothly interpolate between them.
And generate new faces that look realistic, but have characteristics of both originals.
Precisely. Or you can sample points from that learn embedding space to generate entirely new data points that still look like they belong to the original data set. It's not just copying anymore. It's learning the underlying structure well enough to create variations.
Okay, that's a huge step. So we can reconstruct, we can generate variations of static, things like images. But what about things that unfold over time? Language, music, sequences.
Right, because so much human expression is sequential. Language isn't just a bag of words. Music isn't just random notes. There's structure, there's flow, there's context.
And that's where standard feed-forward networks struggle, right? They don't really have memory.
Exactly,
Yeah.
which is why we need recurrent neural networks, RNNs. These are networks designed specifically for sequential data. They have loops.
Loops that let them feed information back to themselves, like a short-term memory.
Sort of, yes. It allows them to process elements in a sequence while maintaining information about what came before. So they can label things in a sequence, classify a whole sequence, or, crucially for us, generate new sequences.
These are the engines behind a lot of natural language processing then, generating text, translation, speech.
Absolutely. But simple RNNs can struggle with long-term dependencies, remembering context from way back in the sequence. That's where more sophisticated units come in, these gated units.
Ah, like LSTMs and GRUs, long short-term memory and gated recurrent units.
You got it. Think of them as having little gates inside that learn to control the flow of information. They learn what's important to keep, what to forget, and what to pass on.
So they can hold on to relevant information for much longer, like remembering the subject of a sentence much later on.
Exactly. It gives them this ability to store information, almost like computer memory, for future use. That's why they can generate much more coherent, contextually relevant text or music over longer stretches. It's not just predicting the very next word based on the last few, it's understanding the broader context.
That ability to link past, present, and future prediction within the sequence. That sounds key for genuine-sounding creative output.
It's fundamental. It allows for that narrative arc, that musical phrasing, that understanding that goes beyond just isolated data points.
Okay, so we have autoencoders learning the essence of data, and RNNs handling sequences with memory. Let's talk concrete examples. What about AI composing music? You mentioned Mozart. How does that actually work? How does it capture Mozartness?
It's fascinating. David Cope's work, Experiments in Musical Intelligence, EMI, is a classic example. Someone called it a musical dice game on steroids, which is kind of fun.
Okay.
So what EMI does is it takes a large chunk of music from a specific composer, say Bach or Mozart, lots of short segments, and it analyzes them to find recurring patterns, motifs. Cope calls them signatures.
The composer's unique stylistic fingerprints.
Exactly, their musical DNA, if you like. Then it uses a kind of musical grammar, a set of rules about how musical pieces are typically structured to recombine variations of these learned signatures.
So it mixes and matches these signature patterns according to musical rules.
Right. Often with a bit of randomness thrown in, guided by the rules to create something new. But because it's built from the composer's signatures and follows musical logic, the output sounds remarkably like a new piece by that original composer. It learned the style and the structure.
That's incredible, learning style itself. Okay, shifting senses now, from sound to sight. AI describing images, it's another form of generation, turning pixels into words.
Indeed. And it's moved way beyond just simple object labeling. Systems like Google's Show and Tell or Microsoft's Caption Bot can look at a photo and generate a whole sentence describing what's happening.
Like a group of people playing Frisbee in a park.
Exactly. Fei-Fei Li's work was really foundational here, inspired by how children learn. The goal wasn't just to label dog, ball, grass, but to get the computer to understand the scene and speak about it in sentences. That's a kind of creativity translating visual complexity into language.
And sometimes it feels almost magical, like it truly sees. But the sources also mention they can sometimes generate nonsensical captions, right? Get things completely wrong.
Oh, definitely. And that really pushes us towards the deeper questions, doesn't it? What does it mean for AI to be creative or to understand?
Yeah, are these systems truly understanding, or are they just incredibly sophisticated pattern matchers? Barbara Gross makes a point about this, suggesting deep learning works well because it's mathematically flexible.
Not necessarily because it's a deeper thinker. It's brilliant at finding correlations and complex patterns in vast amounts of data. But does that equal understanding in the human sense? That's the million-dollar question.
And it ties into that black box problem Judea Pearl talks about, right?
Yeah.
If these systems are so complex and non-transparent,
It can be a hang-up, as he puts it. They generate answers, sometimes amazing answers, but we don't always know why or how. We can't easily peek inside and see the reasoning process, if you can even call it that. It lacks transparency.
which feels very different from human reasoning, even human creativity, where we can often reflect on our process.
Right. And this leads to other big challenges like transfer learning and common sense, which people like Josh Tenenbaum and Oren Etzioni focus on.
That very human ability to take knowledge from one area and apply it to something totally new.
Exactly. We do it effortlessly. AI systems, even powerful generative ones, often struggle with that. They can be brilliant at the specific task they were trained on, but brittle or lost when faced with a slightly different situation.
So, is the hope that common sense might just emerge from even bigger models or more unsupervised learning?
That's one hope, that by learning more about the world from raw data, like a child does, these systems will pick up common sense reasoning. But others, like Etzioni, are more skeptical. He points out that we haven't really seen that kind of emergent, human-like general intelligence just from scaling up data and models so far.
It feels like we've climbed one hill, like Yoshua Bengio's metaphor. We've made huge progress with deep learning.
But now we can see the next range of hills, the next set of challenges. The limitations are becoming clearer.
So what's the path forward then? Especially for more creative AI.
A lot of the focus is shifting towards systems that learn more efficiently, more organically, learning from observation, interaction, maybe even play, with much less reliance on those massive labeled data sets, trying to capture that childlike ability to learn fundamental concepts about the world.
Getting generative models to move beyond just mimicking patterns to maybe having a deeper understanding of the patterns they're generating.
That's the goal, to build systems that can not only create novel outputs, but also reason about them, adapt them, and integrate them with broader knowledge. True adaptability and innovation, not just sophisticated recombination.
Wow. It's been quite a journey today. We started with the basics of learning from data distributions,
Move through autoencoders learning the essence of things,
to RNNs handling sequences with memory.
and saw examples like AI composing music and describing scenes. These deep learning tools are undeniably pushing AI into creative territories.
It really does broaden the definition of what AI can do.
So maybe here's a final thought to leave you with. As these machines get better and better at generating content, images, text, music, code, you name it, what happens next?
What new ways might we collaborate with them? How does human creativity change when we have these powerful creative partners?
And maybe even, how does it change our own view of ourselves, our own understanding of intelligence, creativity, maybe even that spark we call the human spirit as we start sharing that creative space?
Lots to think about. A fascinating and slightly mind-bending future ahead.